So the last thing I promised I would tell you about is inserting elements into a heap. And that turns out not to be all that hard, but it does involve some coding that we haven't done yet. The idea is that a new element that we're going to insert, we stick at the very sort of bottom right corner of the heap. Or if the heap was already full, then the far left. But now we have potentially violated the heap property. So this node to its parent could be problematic. So essentially, we need to do some sort of an analog of down heapify that I call up heapify that takes this value that might be problematic, swaps it up if it is, and then continues to swap it up the tree until it reaches a place where it is smaller than both of its children, at which point the heap property is satisfied globally. So I'm going to leave that as a homework problem for you to actually code up heapify, and that gives us the insert that we need. All right, so now that we can insert and delete into heaps in log n time, we can use this to solve the top k problem that we've been talking about throughout this unit by running through the list of the n elements that we want the top k of. And meanwhile, we keep a heap of size k off to the side. And so we're trying to find the largest k in this case. So each new element that we encounter, we ask, is this element bigger than the smallest value that we've kept so far? So does it deserve to be in the top k so far? If not, we can just throw it away because we know it's not going to be part of the top k. If it is, then the smallest thing in that heap no longer needs to be there because we found something better. So we delete them in and we insert the new value that we just got into the into the heap, and reestablish the heap property by, well, we could do it as a down heapify actually because we deleted the node from the top. We can replace it with something else. So for each of n times, we do possibly one insert into the heap, which is a log k operation. So the total running time ends up being we do n log k operations. So that's actually pretty efficient. It doesn't solve the top k problem better than the randomized algorithm we talked about, the partitioning algorithm, but it does it pretty fast. And there's other uses for this, so and we'll see that in the next unit. Thanks a lot, and good luck with the homework.